Good day to everyone. Today we're going to discuss the list 2 requirements that we're going to consider for the geometric design of highways, and that will be the design volume and the number of lanes. So the design volume and the number of lanes will always go hand in hand in our design of highways. So to begin with this part of Unit 2, so for the design volume, we call this now the design hourly volume or the DHV, which is now defined as the 30th highest hourly volume or traffic volume that will be considered in both directions, and this is taken in the year in which a data was collected. The measurement for design hourly volume will always be by vehicles per hour. So why do we use the 30th highest peak collected in our data? 30th, as this will now be the most reasonable hourly volume that would provide us the best result in our road designs. So, applying our design hourly volume, necessary or appropriate adjustments now may be applied for situations that would involve high seasonal fluctuations. Example of high seasonal fluctuations would be the fiestas or holiday seasons, wherein a certain city or area would now accumulate more vehicles compared to the normal days or normal weeks of the year. So for design hourly volume, we now have values that would be used for two-lane rural highways. And we have the HV will be the total traffic in both directions of the travel. And then for our DHV, for multi-lane highways, this will now be called our DDHV or the directional distribution, in which we are going to consider the direction of the heavier flow. So unlike for two-lane rural highways wherein we consider both directions, the going and the going to and the going away directions, for multi-lane highways we are only considering which among the two directions will contribute most to our traffic. So for the design volume of a two-lane or three-lane two-way highway, the DHV is computed as the product of the AADT and a factor. So for this equation, the DHV is our design hourly volume, AADT is the annual average daily traffic, which is simply the total number of vehicles that would traverse our highway section for the whole year divided by 365. And then for the K value, this is the proportionality constant of the daily traffic that is occurring during peak hours. And this will now be ranging from 12% to 18%, depending on the situation or the condition of our highway. For multi-lane highways, such as your 4-lane two-way highways or your 6-lane two-way highways, we now compute for the design volume as the DDHV, or that is now equal to the AADT times the K times a factor D. So if you are going to notice, the equation for DDHV is now or can be written as AEDT, which is our DHV, multiplied to the factor D. So for this equation, DDHV now is what we call your directional design hourly volume, which is the volume of traffic considered or measured for the lanes that will be, for the direction of lane that will be contributing more on the traffic. And then we have your AEDT as we have defined earlier. And then we have the ADT or your average daily traffic, which can be used instead of the AADT. So the difference between the AADT and ADT is that for the average daily traffic, this is simply the total number of vehicles that would traverse the highway section for a day. Okay? So sa annual, it is the average daily traffic, but we are considering the total of 1 year. So for your key value, this will be again a proportionality constant and will differ based on your condition. So for rural highways, this will be 12% to 18%, and for urban highways, it will be between 8 to 12%. So the D now here is your directional distribution, which is simply a percentage between your directions on your highway. And the directional distribution is the percentage of the heavier or higher volume. So this would usually range between 60 to 70%. For the number of lanes, this will now depend on the design volume under a specified level of service. So once we have identified our design volume, we now compare it to a level of service. And from that level of service, we'll now be able to identify how many lanes we are to place in our highway section or what we are designing. So in considering now the number of lanes, we can follow a trial and error procedure. But take note that for the trial and error procedure, this will usually or should usually be done during the design period and not when your highway is already existing. So for the number of lanes, what we are to consider will be the capacity of the road, which is simply the maximum hourly rate at which vehicles or pedestrians or persons could be expected to traverse a point in our section of a lane for a given time. So it's basically the maximum or the highest number of volume that your highway section could accommodate for a specific time. And then we have your level of service or LOS, which is simply a qualitative description of how a certain facility is performing. So the performance of a facility or your road section will usually be defined by its speed together with the convenience and comfort experienced by the users. So for level of service, we now consider or determine this by the use of our volume capacity ratio. So for our levels of services, we have 6 different levels of service. The first one is what we call the LOSE, which is our free flow service, meaning there is uninterrupted vehicles. So vehicles now will be moving along our road section non-stop. So as you can see from the figure, the vehicles now are not affected by any other vehicles, or their speed, their flow is unaffected by other vehicles. The next level of service is what we call your LOSB, which is known as a stable flow or a reasonably free flow. So it's almost like a free flow, but the flow now is somewhat or sometimes affected by other vehicles. So as you move freely, you could also notice other vehicles moving alongside you. Okay? So medyo dumami na yung number of vehicles natin sa ating road section. So next, we have your LOSC, which is known as a stable flow. So the flow now of vehicles will be affected by other vehicles already. So we have more vehicles traversing your road section, and their speed or their flow will now be affected by the other vehicles moving within the road section. Next, we have LOSD, which is your high density free flow. or borderline unstable, meaning it is near capacity already. So same as LOSC, the vehicle operations now or the vehicle flow is also affected by other vehicles. So we'll have more vehicles traversing your road section at the same time. Then we have LOSE, which is high density traffic flow or nearing capacity. So this is the flow wherein you are at almost the capacity or 100% of the capacity of the road section. So it is an extremely unstable flow. So the operating conditions here would usually be extremely poor. So when you are in a road section under LOSE, you will now be experiencing annoyance throughout your drive on the road section. Okay, next we have LOSF, which is known as the force or breakdown flow. Amount of traffic now will exceed the capacity of the road section, meaning we have more than 100% of the capacity. So if the capacity of the road section, for example, will be 12, then for LOSF, what is inside your road section for that time is already more than 12. Okay, so it's congestion already. No movement of flow or no movement of vehicles. So for the volume capacity ratio that we are going to use to define levels of service, this is now simply the measurement of the operating capacity of your roadway or intersection. So in this, you will simply be computing the ratio between the number of vehicles traversing your section, so that is your volume, divided by the number of vehicles that could theoretically pass through your section at full capacity. Okay, so for your LOS and volume capacity ratio, we now follow this table. For an LOSA or a free flow LOS, the volume capacity ratio will be less than 0.20, meaning 20% only of the capacity will traverse your section throughout your observation or throughout the section. For LOSB, we'll have a volume capacity ratio ranging from 0.21 to 0.5. So at maximum for an LOSB, you have 50% of the capacity traversing on your road section. For LOSC, we'll have maximum is at 70% of the capacity. LOSD will be at 85% of the capacity will be occupied by the road section at most times. And then we have LOSE, wherein it achieved already the maximum capacity at 100%. And LOSF is when your volume capacity is greater than 1 already, meaning the number of vehicles passing through your road section is higher compared to that what is designed as a capacity of your road section. So to help us with the design of our volume and the number of lanes, we will now be using table 6.5a, which would show us the basic capacities for highways and urban streets. So for an urban street, we have to identify your carriage width, and from here we'll be able to see now its equivalent basic hourly capacity measured in PCU. And for urban streets, this will now be considered for both directions of the road. So please take note that for a carriageway width, this will now be defined as simply the measurement from one end to one end of your road section, or the width, lateral width. So if this is our road section, this is divided into two. So we have here one-way, two-way section. So we have one lane two-lane. So this is a two-lane having two-way or two-direction road. So your road width or carriage way width will simply be this width. This is your carriage way width. So it's the length between the end to end of your road section. So if I will have another roadway here, so I have here one way, another direction, opposite direction. So this road here is a 1, 2, 3. So it's a 3-lane. We have 1, 2 way road, and your carriage width will be from this point to this point. So this is our carriage width. Okay, so considering now the width of your road section, then we consider now we will now get our equivalent hourly capacity. So continuation of table 6.5 will be for our highway road type. So for a highway, same, we consider your carriage width, and for each range of carriageway width, you have an equivalent basic hourly capacity, which is also measured in PCU. So another table that could help us in our design of the volume and the number of lanes of a highway is table 6.5b, which shows us the capacities of multi-lane highways for flat terrain having at least 3.5 meters width. So this will be our table. So since for multi-lane highways, they will now be focusing on one direction only. So in this table, you can see that the capacity will be measured per lane. Okay, so if we have a section of the road having 2 lanes for one direction, then you'll have to use this value, in which the total capacity now for the 2 lanes will simply be computed as the number of lane divided by or times the capacity of that lane. Okay? And then for the lane width that we are talking for this value, the 3.5 meters, if we have, for example, your highway section, as we have said, from end to end of your highway section is your carriage width. So the lane width will simply be the distance between or the width of the single lane. So this is our lane width. This is also a lane width. Okay, so basically the carriageway width is simply the sum of your lane widths. Okay, so take note that if the traffic volume provided is a mixed type, meaning it's a combination of different vehicle types, the passenger car equivalent factors will now be applied in order to obtain a volume under a PCU or a passenger capacity unit. Okay? So for the passenger capacity unit or the PCU, this is simply a converted value of the mixed types of vehicles found in the traffic, and we convert into a single unit. Okay, so for different types of vehicles, basically the conversion to a single unit will be based on a car capacity, and the PCU will usually be applied for flat terrains. This table now shows us the different PCU value or PCU factors that we need to apply two different vehicle types. So, to understand the use of your PCU factors, let's see, we have for cars, we have counted 300 traversing our road section. So for jeepneys, let's say we have 220. For buses, we have, let's say, there were 50 counted. Trucks at, say, 23. And for motorcycles, let's say we have 12 traversing. So this one now is our vehicle count, and this is not, so the sum of your vehicle counts is not equal to your EEDT, or the volume of the road section. So what we will do here is to first multiply each vehicle counts with their corresponding PCU value or PCU factors. So for cars, that's 1. We have 1.4, 2.2 for buses and trucks, and we have 0.5 for motorcycles. So we'll not simply add them up to arrive from your vehicle count. So you have to multiply it first. So for this example, we now have our equivalent PCU for our EEDT, or your volume, is now equal to, as computed, 824.6. Okay, so where did I get that again? You multiply first the PCU factors to each vehicle type, and then you add them up. And that is now your equivalent EEDT for that road sections in terms of passenger capacity unit. So again, if you're going to look at our table, passenger car unit would usually be based from or based on the capacity of cars. So meaning, for these numbers, 1.4 would simply mean that a jeepney would have 40% more capacity compared to your jeepney. Pag sa motorcycles, it would simply mean that a motorcycle will have a 50% capacity of the car unit. Okay? So again, we only use this if the given EADT is in terms of different vehicle types. Pero kung naka-convert na siya into a single unit, which is your PCU, then no need to convert your values. So to understand design volume and number of lanes, let us solve an example. So let's see. A proposed highway is to be designed with adequate shoulder and clearance in a level terrain with the following properties. So AEDT is 40,000 PCU per day. We have your directional distribution at 65%. And your K is equal now to 9%. Now estimate the number of lanes that will provide LOS B. So for this problem, we now compute for our volume capacity of the road. Since volume capacity now will define our LOS. So based on the volume capacity that we are going to compute, we'll now be able to identify which LOS that design will be under. And for this problem, we want now an LOS which is under B. Okay? So, for this problem, this will now we will now apply a trial and error method. Why trial and error method? Because we do not know yet what number of lane will provide this. So what we will do is to start off first with the smallest number of lane. So for our computation, we will need now our volume capacity from which we'll be computing the ratio. And from that ratio, we'll arrive at the equivalent LOS. So for our smallest number of lane, we have a 2-lane, 2-way highway. So for a 2-lane, 2-way highway, what this means is we have your road. So it's divided into 2 lanes. And our direction is 2. So towards and away. So that's 2-lane, 2-way highway. So for our volume, that will now be under DHV since it's 2-lane, 2-way. So DHV is simply your AEDT multiplied to the K value. Substituting now our values for 40,000 and 0.09, will now arrive at DHV for a 2-lane, 2-way is 3,600. Okay, and for our capacity, we'll now take this from table 6.5. So this is table 6.5. And what we will use now is the maximum value for your capacity, which is 2,400. Why are we using the maximum value? Because using the smaller values here will result to a higher volume capacity ratio. So we want a smaller volume capacity ratio in order to have a lower LOS or a better LOS. So using now the maximum value, this will now give us the smallest ratio for your volume and capacity. Okay? So since we're talking about highways, even if the maximum value here is 7,200, hindi ito yung gagamitin ninyo. Okay? So for the volume capacity, just simply compute 3,600 divided by 2,400. That will give us 1.5, and that is greater than 1, meaning the LOS for a 2-lane, 2-way for this given properties will be LOSF. So therefore, this is not the number of lanes that we want to have in our highway section or our proposed highway. So with this, proceeding now to our next assumption, which is a 4-lane, 2-way. So this is the next smaller lane or number of lanes that we will have. So for a 4-lane, 2-way, this would look like this one. So if we have here your total length of or total width of the highway, so we divide it into 2 for one direction and opposite direction, and then we divide it into 2 for each direction. So we'll have here now a 1, 2, 3, 4 lanes with 2 directions or 2-way. Okay, so for a 4-lane, 2-way highway, this is now a multi-lane highway. So instead of using DHV, we'll now be using DDHV, which is computed as the product of your AEDT times K times D. And since we have already computed for your AEDT times K, which is your DHV, we just multiply the DHV with your directional distribution. So that's 3,600 times 0.65. The volume now for a 4-lane, 2-way highway will be 40. So that's our design hourly volume. And for our capacity, this will now be taken from table 6.5b. So we have this table already for a multi-lane highway. So we have to consider for a DDHV, we are only to consider which of the directions will contribute our traffic. So only one direction. So we'll choose this direction. Okay. So to solve now for the capacity of the lane, we'll now be using how many lanes can we see for one direction? We have 2. So we'll be using this value. So this is the capacity per lane, 1,800. So how many lanes do we have? We have 2. Therefore, we'll now simply compute for the capacity as 2 times 1,800, giving us a value of 3,600 ECUs. So for our volume capacity, that will simply be 2,340 divided by 3,600 equal to 0.65. And from our table of LOS, a 0.65 volume capacity is equal to an LOSC. So still, a 4-lane two-way highway is not adequate for our property of our proposed highway. So we will again move to our next assumption. So for our next assumption, we'll now be using a 6-lane two-way highway. So for our 6-lane two-way highway, this will now be one lane. We divide it into 2 directions, and for each direction we will have 3 lanes. So in here we have now 1, 2, 3, 4, 5, 6 lanes with 2 ways. And 6-lane 2 ways is a multi-lane highway. So therefore, we'll use again for the volume the DDHV. And since it's already computed from 4-lane 2-way, DDHV of 6-lane 2-way is also 2,340. So what will change only is the capacity of a 6-lane 2-way, the theoretical capacity, which will again be taken from table 6.5. So from table 6.5, again, for a multi-lane highway, we will only be considering one section of or one direction of our highway. So let's consider this direction. Okay. So looking at this, how many lanes can we see per direction? We have 1, 2, 3. So in here, we are going to use now this value. So for your capacity, we'll now have 3 times 1,750. And that's equal to 5,250. So computing for your volume capacity, that's 2,340 divided by 5,250, giving us an answer of 0.446, which is between LOSB. The range is 0.21 to 0.50. So it is within the range of LOSB. So therefore, our answer now should be a 4-6-lane two-way highway. So this is our design for our proposed highway with a property of 40,000 PCU per day with 65% distribution per direction or for the higher direction. Okay? So another example, a highway with a carriage width of 4.5 meters has an EEDT of 12,000 PCU per day. So if we have a K value equal to 12% and a distributional percent of 60%, is the highway now capable of handling the traffic? Likewise, what value of K would cause the highway to halt? So for the first question, is the highway capable of handling traffic? So for our solution, we have to compute for your volume capacity ratio. So we have to solve first for your DDHV. So we'll assume that this is a multi-lane highway. So for your capacity, we'll be taking it from table 6.5a for highways. So it's given that our carriageway width is 4.5 meters. So we'll be using this values. So for a 4.5 meters, its hourly capacity is equal to 1,200. So from here, we can now solve our volume capacity as equal to our AEDT times K times D divided the theoretical capacity, giving us a volume capacity of 0.72, which is less than 1. Therefore, our highway is capable of handling traffic. And if you are going to be asked what is the LOS of this section, then this section will be under LOSC, which is 0.51 to 0. This is LOSD, which is 0.71 to 0.85 range. Okay, so for the next question, what value of K will halt the traffic? So we will still be using the same equations and the same value of our capacity. So we'll be solving again VC equal to, or V over C is equal now to 12,000. And since we are solving now for the value of K, so this is unknown, times 0.6 divided by 1,200. So in this case, the volume capacity ratio that would halt our traffic will be equivalent to 1, or meaning we have approached the capacity already of the road section. So substituting now, 1 is equal to 12K times 0.6 divided by 1,200 will now arrive at a value of K which is equal to 0.167. So for the next example, how will the design volume vary for an urban highway of AEDT equal to 3,500 vehicles per day? So for our solution, we'll just be solving the daily or design hourly volume, which is K equal to AEDT. And for the values of K for an urban highway, as we have discussed, is equivalent to 8 to 12%. So from here, we'll just simply compute for the minimum and maximum values using our percentages. So for K equal to 8%, we'll now arrive at a K, or at a design hourly volume, which is equal to 280 vehicles per day. And for your K value equal to 12%, we'll now arrive at a DHV of 420 vehicles. So when designing now the volume of a road section, typically we would want to have a higher capacity. So if we are solving for a capacity, then we want to use a higher K value. But if you want to minimize the number of vehicles that would traverse a road section, so that we will arrive at a lower LOS, then we have to use a minimum value. Okay? So we have another example. A two-lane, two-way highway has a volume capacity ratio of 0.75 during peak hours. If AEDT is expected to increase at a growth rate of 1% per annum, when should the highway operate as a four-lane, two-way, or a six-lane, two-way highway? So consider the peak hour factor is 10% and the directional distribution is 65%. So as a hint to solve for this problem, it means that we have to improve the highway when the volume capacity now would reach 0.9. So for our solution, what we have to do, assuming that the lane width is equal to 3.5 meters, so we'll now use this table. So at lane width of 3.5, we are given a two-lane, two-way highway. So meaning the total carriageway will now be 2 lanes times 3.5 meters, or that's equal now to 7 meters. So in that case, we'll now be using this value for our basic hourly capacity. So with that, what we will do first is to compute for the AEDT of the present two-lane, two-way highway. So given now an LOS, or a volume capacity of 0.75, that's equal now to your DHV divided by the capacity. So that is DHV is AEDT, and we multiply it to 0.10, which is our peak hour factor. So in here, we're only assuming first our peak hour volume. So for our peak hour volume for the AEDT, that is now equal to 18,000 PCU per day. Okay, so that's for our AEDT. So meaning, at present, with 0.75 volume capacity ratio, we now have a present number of vehicles passing through our road section for the whole year as 18,000. So with this, we now solve for your future volume. So for the future volume, since this is a two-lane, two-way highway, and we want now to know when we are going to expand our road section. So if we are going to expand, so we simply start our expansion with the next higher number of lanes, which is a four-lane, two-way. So with this, we'll now be using table 6.5b. So 4 lanes, so we'll be using a one direction. So per direction, that will be 2 lanes. So this is our capacity. So AEDT for the future will now be equivalent to 0.10, which is our peak hour factor. So the peak hour factor, if we do not have a key value, we will use your peak hour factor. So multiply 2.65, which is our directional distribution percentage. So divided by 2 times 1,800. And we want now to assume that for a 4-lane, when we improve now, that 4-lane two-way highway will experience a 0.9 capacity, which means we are at LOSE. So, okay. So with that, we now compute for AEDT for the future, which is equal to 49,4846 or 40.15 PCU per day. So once we have solved for your future AEDT and we have solved for your present AEDT, we can now apply this equation, F equal to P times 1 plus I raised to N, which is simply an equation for growth rate. Okay, so this equation will be familiar to you when you are computing for interest or money interest. So this is the same concept with our growth rate. So we are given the growth rate of your AEDT per annum. So for this, we now substitute our future and our present. We'll have 49846.15 is equal to 18,000 plus 1 raised to your growth rate 0.01 or 1% per annum. So raised to N. And now here is the number of years it would take for us to reach this future AEDT. So with this, N now is equal to 102.36 years. So meaning, a 4-lane two-way highway will operate for 102 years or after 102 years. In that case, it is best to design the highway at 4-lane two-way already in order to avoid a LOSE within 100 years. Okay. So next, if we use now 18,000 PCUD, the current or the present AEDT for a 4-lane two-way, so using this table again, so it's a 4-lane, so we still have the capacity 2 times 1,800. So we'll now be arriving at a volume capacity of 0.325, which is equivalent to, in an LOSB, which is between 0.21 to 0.50 from our table. So this means that a 4-lane two-way highway at present will encounter in an LOSB as compared to the present 2-lane two-way, which is experiencing a volume capacity ratio of 0.75, which is LOSD. Okay? So, ibig sabihin, it's better now to have a 4-lane two-way highway while it is still at 18,000 PCU. Okay? So, it's ideal now to begin our design of 4-lane highway at present, since expanding 4 lanes after 100 years will be very complicated as there is now the presence of existing establishments in the future. So basically, mahirap nang magkuha ng right of way later on if we want to expand our 2-lane highways or 2-lane two-way highway into a 4-lane two-way highway. So for a 6-lane two-way highway, parang okay, hindi na natin kailangan compute kasi okay naman na yung 4-lane two-way highway natin. Kasi kaya na niyang mag-reach. So, 100 years pa bago niya ma-reach yung 0.9 na volume capacity or yung LOS na E, which is unstable. Okay? So, that's it for design volume and number of lanes. Okay? So, for your references, you can always check the book of Sigwa and the following sites for geometric design. For your evaluate, answer the evaluate question under design lane and design volume. Thank you for listening.